Today we're going to be talking a bit about Brownian motion, geometric Brownian motion, Monte Carlo methods, random walks, things of that nature. So it all began back here with this, right? This is pollen. And about 2,000 years ago, about 2,000 years ago, in fact, almost exactly, this guy named Lucretius was watching pollen float around in the water, and he described the motion perfectly. He had no idea what caused it, of course, because he was a 2,000-year-old Greek philosopher, but he described it perfectly. And then came this guy named Robert Brown. Right, it was a Scottish botanist who looked at this stuff for a while and tried to figure out what was going on. And then he described the motion of pollen in water and how it seemed kind of random. And this French mathematician came along a few years later, about 100 years later, in 1900, named Louis Bachellier, I suppose. It's been a long time since I've done French. Don't hate me too bad. Who started actually making mathematical models about how this random stuff moved, right? Because the pollen looked like it would be in a place, and it would jump over here and jump over here and jump over here. There was no rhyme or reason to it. And a couple years after that, in fact, about 1905, our favorite guy came along, Albert Einstein, and his first significant scientific paper was about Brownian motion. So what we see up here is the German word kind of having to do with motion, and then down here is Brownian molecular motion. That's what he was talking about. I have no idea what the rest of the paper is about, but even our guy Einstein was big into Brownian motion. Here's the behavior of Palantir over the last 2 years or so. So a lot of stuff going on here, right? It starts low, and then it jumps up, and then it jumps all over the place, gets higher and higher, it dips down. Wouldn't it be cool if we had a way to try to describe how this motion was happening? And that's where random walks and Brownian analysis come in. So the first thing we're going to do is run about 1,000 simulations based on the history up to this point, midway in the plot, to see, given what we just seen, what's going to happen in the future. Now, obviously, if you look at this, it totally missed the big jump upwards, and we'll talk about there's two general categories of places where Brownian motion, with this type of random walk prediction doesn't really take into account what's going on. Right, and then if we look at the first and second standard deviation away from this 1,000 simulations, right, the bulk of the simulations thought that the price was going to stay kind of level. Another standard deviation away thought there's a little up and down wiggle room, and then we're out in the very edges where actually our simulation did catch what's going on here, but this is more than 2 standard deviations out. So we really wouldn't have made a bet that that's what was going to happen. So let's think about that. We'll come back to that later. But in the meanwhile, this is a really useful technique for getting a basic intuition about how an equity will behave and maybe where it's likely to be in the immediate future, provided a couple of interesting things don't happen. So what is a Monte Carlo simulation? We'll start with the arithmetic version. Looking at this, right, all this is saying up here is this is the +1. This is what's going to happen tomorrow. The S of time t, right, is this is what's happening today. And then we've got 2 terms in here that are interesting. It's really just 2 things. That's all that's going on. This first term is talking about drift. And by drift, what we mean is if we were to go and just draw a couple little lines over these different regions, you see that the stock is on average, it's tending to go up, and then it's tending to go up steeper here and steeper here. And then maybe if we drew a line through the whole big thing, it would look something like this. There's an important takeaway here, which is depending on where we're looking at this equity, the drift might be different, right? So that's really interesting. How long a window can we look at? How short a window can we look at? Can we look at the last 5 years? Can we look at the last 5 days, 2 weeks, 1 month? What becomes useful to try to figure out what will happen in the future? Then the last thing that we'll look at here is this funny term at the end. And all this is saying, right, the sigma square root delta t, the delta t is just talking about the time. We're talking about 1 day, so really just forget about that. It's just a 1. All we're doing, and this is all this is going along and measuring how wiggly the stock price is on a daily basis. How much does it jump around, right? And we go all the way through and just measure how much this thing jumps around. So it's easy to tell, though, even looking at this with your eyeballs, sometimes it's jumping around more than other times, right? And this is a problem of this type of analysis, and we'll come back to a couple of the shortfalls in a bit. And we talk about this using lowercase sigma. It's a Greek letter, sigma. A lot of times in statistics, you'll see this used to mean variance, right? Standard deviation. When you're talking about those sorts of things, you'll see this all the time. And a lot of times then, all we're really talking about is how jittery something is, how much is jumping around. That's all it really means, right? So now when we look at this, we know what's happening. We know where this is coming from. This is where those bands are. We just use that formula, run 1,000 different simulations and see what happens, right? How many of the simulations show it being this tight thing? How many are a little wider? How many are a little wider? Which brings us to geometric Brownian motion. So almost the same idea, right? We've got a little different notation, but the same idea of the value on the left is going to be today's value, right? The ST that we're starting with. And we're going to do a couple of things to it. So this first term that's popping out here is the same drift that we had before, right? So we use the Greek letter mu, so it's the little thing that looks like the U there, just to talk about this drift. But there's just one thing a little different here, which is notice they bring a little of that variance in that sigma term. That's all that means, right, is how much it jumps around. So if this thing is jumping around a lot, they're damping the drift just a little tiny bit. And the reason they do that is because that looks more like actual deviations of stock prices in other natural phenomena. And a bunch of mathematicians realize this over time. We do this one little tweak, the thing just works better. That's all that is. Second part, right, when we think about the variation over time, about this variance, it works exactly the same as the other one. We're just going and really measuring how much stuff jumps around. That's all it is. And this last little bit on the end, the z, well, that means the same thing as the epsilon t in the other one. And the difference is the geometric Brownian motion comes from a branch of math called stochastic calculus. And like almost every other domain in life, there's tribes of people who like to talk about things in a certain way. This is how they like to talk about random normal numbers versus how the other guys do. So what this experiment did is we took what was a 20-day assessment window and a 20-day simulation window and looked across everything during this period of time. And the question that we're asking is how often is the simulation completely wrong? Is the actual share price 20 days in the future potentially totally outside of all the simulated bands? And there's a couple little spikes where we hit 40% of the points during that window, so that's pretty bad. But the rest of the time, it's within the prediction. So this is interesting, right? The bulk of the time, this does a pretty good job of representing where the price will be in the future, but not always, right? There's a couple scenarios where it doesn't. Let's see what we come up with in terms of a general prediction, what will happen over the next 3 weeks. 3 trading weeks, 4 trading weeks. And this is it. This is what we see. So the question is, are we going to, at the end of about a trading month in the future, see a price that is largely in this band? There's 2 broad categories of things where this type of simulation or this type of modeling is going to fall apart on us. The first one is things that some people call discontinuous events, discontinuities, something like that. And the idea is, imagine an event that we didn't know was going to happen. An earnings report, a scandal, a this, a that, a product recall. This is, of course, not going to be able to predict that. The other thing that this doesn't take into account, in fact, there's two parts to this, is that variance, that sigma term, it actually varies over time. You'll notice there's time intervals where it's very calm, almost every stock, and then there's times where they'll start jumping around a lot more. This method doesn't take into account varying volatility, right, or varying variance, really, if you will. It also doesn't take into account differing drift over time. So think about it in terms of background radiation. All of us on Earth, as we sit around, are bombarded with radiation from the soil beneath us, from cosmic rays, from everything else that's happening. And absent other sources of radiation, we can measure it. And it's also going to be sort of randomly distributed in similar ways to the Gaussian Brownian, other way around, to the geometric Brownian methods. But it's this background. It's this background jumble, this background noise, kind of describing how the radiation moves around. Think of that in the same way that geometric Brownian motion is. It's the background radiation. It's the background rumble of how these equities move around. But if your neighbor buys, a surplus container of uranium off eBay and hucks it over your back fence, you're going to get a lot more radiation than you were getting before. These are the discontinuous events that this doesn't model. But think of this as just a background rumble, a background noise simulation for an equity going forward based on what appears to be random behavior that we can use as a foundation to put more interesting stuff on top of. Keep calculating.